In this video, we're going to be taking a look at a set of MATLAB code I developed to calculate the natural frequencies and mode shapes of an in-mass spring mass system. In addition, this script will numerically solve the equations of motion to graphically display the position of the masses as a function of time in the desired mode of vibration. In my previous video, I displayed a set of animations that I created using MATLAB, and I discussed the eigenvalue problem and how this relates to a spring mass system and the modal response. So if you haven't checked out that video, please do, as a lot of the math that I reference here was discussed in detail in that video. So the purpose of this video is purely just to discuss the MATLAB script, and I will not be going in depth on any of the math. So we start out here with our problem parameters. We have m, which is the mass of the carts in our system, k, which is our spring constant. Then we have the number of masses. This code is valid for an infinite number of masses. Here I'm just using 2. We have t, which is our simulation time. So how long do we want to solve for the motion of these carts? And then our mode. This is just the mode that we want to observe the motion in. And note that whatever mode number you choose must be less than or equal to the number of masses in the system. So the first step here is to create the mass and stiffness matrices based on the generalized free body diagrams. We discussed the free body diagrams and the matrix form of your mx double dot plus kx equals 0 differential equation in the previous video. And we determined that the mass matrix is basically the mass of the carts multiplied by an n by n identity matrix. And then the k matrix is an n by n matrix with 2 times k along the diagonal and negative k on the sub and super diagonals. To create the stiffness matrix in MATLAB is a little bit tricky. You have to use the spdiags function, which if you go to the MathWorks documentation, you can see that basically I just used the code from the tri-diagonal matrix example, where we have a matrix with a certain value on the diagonals, but then also we have a different value on the sub and super diagonals. And this k matrix that we create is a sparse matrix because we use the spdiags function, so we have to make it a full matrix, which is why we have this k equals full k. So the next step is to solve the eigenvalue problem associated with the natural frequencies and mode shapes. So we use the eig command in MATLAB to return our eigenvectors, phi, and our eigenvalues, lambda. And here's the general form of the eigenvalue problem that we're solving here. Phi are our mode shapes. So each column of phi that we can take a look at here represents one mode shape. So for this 2-mass system, column 1 are the displacements that lead to your first mode shape, and column 2 are the displacements for your second mode shape. And then lambda is the square of our natural frequencies. So then in the next line we find our natural frequencies by taking the square root of the eigenvalues. So we've successfully solved the eigenvalue problem here, and so now it's time to iteratively solve for the motion of these carts using Euler's method. And so we set up a little bit of time step stuff, get our total number of iterations, and then set up a time vector for plotting. Then I'm going to pre-allocate my position, velocity, and acceleration vectors, and the initial displacements of this motion will be governed by our desired mode. So if you're looking for the nth mode of oscillation, then we're going to take the nth column of our eigenvectors as our system's initial displacements. We're going to iteratively solve the equations of motion using semi-implicit Euler, which is a reformulation of traditional Euler's method for solving differential equations. The equation here for the acceleration of the carts was derived in my previous video, and then we solve for the velocity and position, noting that the new quantity is the old quantity plus the rate of change times some increment in time. And then we just plot our results using standard MATLAB plotting syntax. So say we have a 5 mass system and we want to look at the fourth mode shape, we can do that, and we can run this, and then we'll get a plot. Here you can see that there's only 3 separate paths of motion, so a couple of the carts move together. You can see that one of the carts doesn't move at all. That would most likely be the middle one, and then the outer ones oscillate in pairs. We could change this to the 5th mode if we wanted to see what oscillation in mode 5 looks like. And you can see once again there's only 3 carts that are oscillating, or 3 different patterns of oscillation. And so we can do this for any number of carts, any number of modes, and you can take a look at what the position of velocity and acceleration looks like as a function of time. So anyways, I hope you've enjoyed this video. Please do go check out my previous video, which is linked in the description, that discusses the math behind this and how we got to this eigenvalue problem and the equations of motion. And this MATLAB code will be linked in the description below. So thank you very much for watching, and we'll catch you next time.